Hello all, how are you? Hope you guys are doing great. My name is Anto. I'm here to talk about Fuzzcube. It's a neat little tool that I recently wrote to help with my fuzzing needs. I'm a security engineer and a developer, and I love research in mobile, especially Android and iOS. I also do some research in Linux and web and occasionally play CTFs. Nowadays, I play a lot more of CSGO. Let's talk about distributed fuzzing with k8s. And to start, let's start with what's fuzzing, right? So we have to understand the basics. Fuzzing is an automated software testing technique where we provide invalid input to a program and monitor it for crashes. So why do we do this? We write a lot of today's programs in memory unsafe languages like C or C++. And having a memory corruption in any of these programs can result in code execution or total failure of the program itself, which can lead to denial of services by constantly crashing the program. These are only some of the few things that you could do with memory corruption. There can be a lot more serious damage done depending on the context in which the program is used. So it's important to fuzz the program that you write, especially if you are writing it in a memory unsafe language. It's not just buffer overflows, but underflows, integer overflows, underflows, like off by one. There is a lot that can go wrong right here. So we use tools like AFL, which is the American Fuzzy Lob, and libFuzzer to fuzz the programs. These are well-known tools and we have great write-ups if you want to get started. I use AFL for fuzzing binaries. As you can see in this picture, which is taken from the AFL blog, it's fuzzing read PNG file. And this is an executable which reads a PNG file from the disk, and it basically mutates the PNG file and it checks if the binary, which is the read PNG file, crashes. That is what it is doing. So as you can see, we have one unique hang, and it has explored 195 unique paths. So what is total paths of 195, right? So think of it as basic blocks. When you provide an input to a program, it goes through a certain steps, right? So if it's a file parser, in this case, it will try to read different parts of the byte stream and try to parse it in a specific way. And there is a lot that can go wrong in that process. So what we are trying to do with AFL is that if you have the source code, we compile it with the AFL compiler, which adds instrumentation into the binary that it produces. This helps the fuzzer in getting some feedback while we fuzz rather than dumb fuzzing. AFL uses this feedback to improve its input so that it can explore more branches. That's a very high level and explanation of how AFL works. A lot can be said about libFuzzer. The same feedback is in here, but libFuzzer does something very different. If you want to fuzz a library, a specific function in the library, I would go for libFuzzer. The reason why is that it is really fast because it is in process execution. Rather than executing the whole program or the binary, it executes the same function over and over with arbitrary input. This is a lot more faster. And in this picture, you can see that that is what is going on. It uses various mutation strategies and it uses that feedback to guide its fuzzing. So when you talk about distributed fuzzing, we have to understand that there is a storage part to it. And ceph is the storage platform that we use for storing the crash results, the fuzzing results, and synchronize them between all the containers that we would use in distributed fuzzing. And just like that, we need containers, right? And Kubernetes is an amazing orchestration tool that one could use to manage all these containers. As we scale the number of containers, it becomes very difficult to manage them one by one. So what we could do is leverage Kubernetes to basically do the management for us or make it just easier. This is what the YAML spec looks like to deploy a libFuzzer into our cluster. So I want to go back and explain this a little further. So we have a lot of containers and they are ready to do the workload that we give it. The way we give our containers some workload is through deployments. So in this case, our deployment is a libFuzzer deployment. And this is basically what you will have to write. You don't have to write it. You just have to modify bits and pieces over here to deploy your own fuzzer. You are not limited by libFuzzer or AFL. It's very simple. So let me go over that. In the first two lines, uh, it's basically standard Kubernetes. We can just copy paste that. The name indicates what the name of the deployment is. Labels help you identify things. And the important bit is towards the spec container section. Over there, I'm referencing an image. It's an image hosted in Docker Hub where you can host images for free. And my container images live there. So when you deploy this YAML spec for the first time, it will pull the image and you can use that image to start fuzzing immediately because that image has AFL and libFuzzer built in and it has I have already compiled libpng so that you can get fuzzing immediately. If you want to add your own programs to it, you are more than welcome to do so. Just pull the container image, it has all the tools you need, and add the program that you want to fuzz into the container. You can upload it, or you can just reference this image locally in your deployment. The next line is the command line. Command. So that is basically the path to your fuzzer because we start this as a container. The container needs to know what program it will execute. So that is basically what it is. And arguments basically means the arguments to the fuzzer. We need a privileged context for this programs because instrumenting and basically monitoring for crashes requires monitoring a process and that requires privilege. The volume mount basically means the shared folder that is being used in all the pods. So if a program writes to sync dir, it is available in all the other pods almost instantly. And that is through ceph. That is why we have a persistent volume plane called ceph fs. And you don't have to change anything over there. Just have your fuzzer use sync dir, which is in the root directory. Right. This is an example of a debug pod that you could deploy, which will give you a shell. As you can see in the command section, I'm executing bash. So using that, you can get a shell and inspect and debug any problems if you have any. All right. So we'll put this all together and we have first cube. To iterate, we use Docker, we use AFL, we use libFuzzer, we use ceph for storage, and we use k8s for orchestration. If you want to monitor your fuzzing workloads, you could use something like Elasticsearch or Metric Beats or Kibana. These are ready to go tools available to the Kubernetes ecosystem, and that is what makes this really great. So you can use any tool that is available to Kubernetes and make that, just basically make this work in however fashion you like. All right, let's look at some demos. Right. Okay. So you can grab the program from that GitHub URL, and it's very well documented. I I have example commands that you can basically copy paste and get running. So that is what I will be doing right now. I'm going to git clone the repo. You could follow along if you like. It takes a while, and once you have it, you have all the pieces necessary to go. It's a bunch of YAML files. To use this, you need a Kubernetes cluster, and the easiest way to do this is to use Minikube. If you are trying this in your own laptop, that is what you would use. It is available for Windows and Mac and Linux. If you are using AWS or GCP, feel free to use the Kubernetes environment they offer. This will work just fine. kubectl is the client's CLI that you would use to talk to the Kubernetes API. You can use the commands that you see here to view the status of the pods and deploy resources into your Kubernetes cluster. As you can see, that is what is happening right now. This might take a while. It depends on where you are deploying it. If it's a server, it will be really fast. If it's your MacBook or your laptop, it just depends on the processing power. Now that we have the deployment done, you can see that we have a bunch of pods, which are containers in our Kubernetes cluster. We just deployed dashboard, the Kubernetes dashboard, which is a UI using which you can look at various resources in your cluster. It is extremely helpful to debug and visualize things. As you can see, I just deployed AFL with one click, with one command. And you can scale them, you can make changes to this deployment from the UI or using the command line. You can see that the command line arguments for the AFL pod is listed right there. AFL uses a master-slave architecture, so you would have one master and a bunch of slaves, and you would scale the slaves, the number of slaves. And it's so easy to do that from the UI or from the command line. As you can see, we have two fuzzers running right now, and you can basically do an ls on the sync directory to see what's in there. It basically will record all the crashes and the fuzzer status, and this can be synchronized to other fuzzers so that they can use this information and make fuzzing much more efficient. This is an amazing use, and thus makes scaling sensible. As you can see, now we have 3 pods fuzzing the program using AFL, and you can visualize that using the AFL WhatsApp command. As you can see right there, we have 3 fuzzers alive, and it's working great. You can look into the contents of the directory, which will contain crashes and status information of the fuzzing. Now we are deploying libFuzzer. It just took a second, but we have the fuzzer right there. And we can scale this fuzzer just like we scaled AFL. It's really simple. And we can look into the command with which it has started right there, which is the libpng fuzzer. And it will also use the sync directory for synchronization. So let's look into that. So here we can see the logs from the fuzzer, and you can see the strategies deployed by the fuzzer to find new paths. So just by clicking through this UI, you are able to do a lot. Now using that button, you can exec into that container, and you can see the data that is being produced by the 3 pods which are fuzzing using libFuzzer. Here's command will tell you the command that is being run right now. Now let's look into how we can scale libFuzzer. It is just like you would scale anything else on Kubernetes. You click on the scale icon, and then you give in the number of pods that you would like, and it takes a while, but as you can see, we have it running. This UI will show you the CPU usage and the memory usage of the fuzzer. All fuzzing results are stored in the sync directory, and you can take a look at it using any of these pods, or you could just deploy a debug pod to it. So that was the demo. We have this documented in GitHub. If you have any issues, feel free to reach out. So that brings us to the end of the presentation. If you have any questions, feel free to ask me any of those on Twitter or GitHub. Thank you so much for your time, and I'll take any questions right now. Thank you.